Welcome. Let me remind you that we have been discussing distances in the context of cosmology, and let me start off by recapitulating the things that we had discussed in the last class. So we started off by looking at the cosmological line element in terms of the conformal time eta, and the advantage of the conformal time is that the propagation of light in comoving coordinates looks like straight lines if I draw it on a space time diagram where I use eta instead of the usual cosmic time. That is the big advantage of using this conformal time. And let me also remind you that there are two different functions over here which come into the line element. One is the r and other is s. If the metric is spatially flat, then r and s are same, otherwise they are two distinctly different functions if the space is curved. And the significance of this I had explained in the last class. R is the distance, so let us take another point over here, a galaxy, let us say over here. R is the comoving coordinate to the galaxy. So if I consider a sphere of radius r, the surface area of that sphere is given by 4 pi into this squared, because this is the thing that multiplies the solid angular terms. So the surface area of the sphere is given by 4 pi s square in general, and the distance is r. So the ratio of the surface area to the distance squared, radius squared, is not a constant, it is a function of r. That is the way the curvature of space manifests itself, and this ratio becomes a constant when the radius is much smaller than the radius of curvature, comoving radius. You recover the value 4 pi, but if the space is curved, as you approach the length scale, the comoving curvature length scale, you have significant deviation in this ratio from the value 4 pi. Okay, so there are two things over here. This is the radial distance, this is the transverse distance effectively. Okay, and the physical situation that we considered, let us move on to that. So we were considering a physical situation where there is a galaxy from which we are receiving radiation, and the radiation is redshifted. The observed redshift is z, and we have seen that this redshift will be the ratio of the scale factors between the epoch when the light was emitted and the light was observed. And the comoving distance to this galaxy is equal to the c into the difference in the conformal time between these two events, and we worked out how to calculate this. So to calculate this, you have to carry out this integral. This integral allows us to determine the comoving distance to any source whose redshift is known. Usually in cosmology, redshift is the observed quantity, everything else has to be determined from the redshift usually. So if the redshift is known, you can use this formula to determine the comoving distance, also the difference in conformal time. And the way to use this formula, you have the Hubble parameter as a function of scale factor here, so one has to use the dynamics of the equation of the universe, which depends on the constituents of the universe, to determine this. And we had worked out one particular example. The example that we had worked out is where omega matter is 1, there is only matter in the universe. And for this model, we had seen that the comoving distance goes as 1 minus 1 by square root of 1 plus z into 2c by h naught. Let me show you what this looks like. We had drawn this in the last class. Let me show you here in the graph what this looks like. So you see that it increases initially as expected according to Hubble's law, this we had checked, we have seen that when redshift is extremely small, this is the same as Hubble's law. We had worked this out in the last class, and then what happens is that as you go to larger redshifts, there will be deviations from the linear relation because the dependence is different, and finally you find that at very large redshift it saturates, it is a constant value. Okay, and we had also discussed the implication of this. This implies that the redshift infinity corresponds to a finite distance. That finite distance is the horizon. That is the furthest distance that we can see, observe at present. A photon which was emitted at the Big Bang will, from this surface, will reach us now. Okay, and we had also introduced a length scale called the Hubble radius c by h naught, and in this particular cosmological model, the horizon is twice the Hubble radius, and we can make an estimate of how much this is. So let us quickly do this. This is a very important number. Let us just quickly make an estimate. So the Hubble radius c by h naught (3 into 10 to the power 8 meters per second), which we can write as 10 to the power 5 kilometers per second, that is the speed of light, divided by 100 h kilometers per second per MPC. So we see that the Hubble radius has a value which is 3000. Here we have 100, here we have 10 to the power 5, so it is 3000 MPC, H inverse MPC. And the horizon in this model is twice this, 6000 megaparsec, H inverse megaparsec. So the furthest distance that you can see in this omega matter equal to 1 cosmological model is 6000 H inverse megaparsec. That is the size of the horizon. Another point to note, which I have mentioned earlier also, that the entire distance scale crucially hinges on this factor H inverse, on the Hubble parameter. If the Hubble parameter is smaller, all the length scales are larger. Hubble parameter is larger, all the length scale inversely related. Okay. So this is just a numerical estimate. Now let us go back to this picture. So here I have drawn this function for you. So the function that I am showing over here is essentially this, where we have worked out the integral which allows us to calculate, we have worked out this integral for the particular cosmological model where omega matter is 1. In this picture I also show you another the units here are megaparsec. Okay, I have chosen Hubble parameter H10 70, and the models are both spatially flat. I have also shown the comoving distance r for another cosmological model which has only cosmological constant and no matter. You see the difference. So the way the comoving distance varies with redshift is crucially dependent on the cosmological model that we have, through the dependence of the Hubble parameter h on the scale factor. The scale factor has different dependence on a for different cosmological models. Okay. The other thing that is important, which I should also show you now, is that you have another function which is s. You have two functions coming into the picture, so we have one more function which is s. Let me also show you how s behaves with redshift, because given the redshift you can determine r, and for the r you can determine s. If the model is spatially flat, s and r are exactly same. Okay, but if the model has curvature, then they will be different. So here the entire discussion, subsequent discussion, is going to be in the context of these 4 cosmological models. We have given them names. Okay, so I will request you to keep this in mind, that there are 4 cosmological models in the context of which we are going to have the discussion. The first one is the standard cold dark matter cosmological model, and this has omega matter not equal to 1. Okay. So the entire universe is filled with dark matter. I have told you that there is evidence for dark matter, and this is a model where we assume that the entire universe is filled with this matter, so that there is that it is exactly equal to the critical density. Okay, we do not see so much matter in the universe, so let us assume that it is dark, and this is the model. This is another model where there is more density than the critical density. Okay, and in addition to this, the universe is, so if there is more density than the critical density, the potential energy is going to be negative, which will make the universe collapse, and this model is going to be spatially curved. Omega curvature is negative, so it is going to be spatially curved. Okay, so the total sum total of these two has to be 1, so this is the contribution from curvature. So this is a model which I am calling KCDM, curvature. It has some curvature which is positive. The third model is open CDM. This is a cosmological model where omega matter, the matter contribution, pressureless matter, is 0.3. There are observations which indicate that this is the matter contribution at present is around 30% of the critical density, total matter contribution. Okay, so the rest of it we are assuming here is in curvature. And this is a fourth model where again omega matter is 0.3 and the and the rest of it is in the cosmological constant lambda 0.7. Okay, this is called lambda CDM, LCDM. Let me also mention that this is the currently favored cosmological model. Observations seem to favor the last one. So let us now see what is the behavior of this function S as a function, how does it behave as a function of redshift for these 4 different cosmological models. Okay, and this picture shows you exactly that. So you see in this model, in the curved one which has got which is positively curved, the S function S is basically sine, and for large redshift this will grow slower than the linear sine function. It grows slower than the linear function as theta, sine theta. For small theta it is linear and then it becomes slower. So you see this model falls below all the other models. Okay, the model over here falls below all the other models, K CDM. And then we have the standard CDM, which is completely matter dominated, has only matter in it, and here we have the open CDM and the lambda CDM models. The value SZ are comparable, but again you see that at low redshift the lambda CDM model dominates, whereas at it is reversed at larger redshifts. And this shows you the same function plotted over a large redshift range in a log scale. It is the same function, but plotted over a large if you want to display some function over a large redshift range, obviously you cannot use a linear scale, then you will only see the behavior over a small part of it. Okay, so this shows you the same function over a large redshift range all the way to redshift 1000, and this shows you the behavior of the different functions. So you see, if you look at around redshift 1000, the open CDM model, the SZ function increases much more, is much higher than the other 3 models. Remember, this is a log scale, so a small increase, this is an increase of 10 times. Okay, so this is more than double. The difference between this and this is more than double. Similarly, the difference between this and this is roughly double. Okay, or more possibly, roughly double. So the point I am trying to make here is that both R and S have depend for the redshift dependence of both of these things is different in different cosmological models. Okay. But then I told you that comoving distance is not a physical quantity. The first physical quantity that you can define is the proper distance, which is the actual physical distance between 2 points, but again you cannot measure this. So for the observational point of view, the important thing is first important thing that we discussed is the angular diameter distance. And let us recapitulate how the angular diameter distance is measured. The angular diameter distance is defined so that if I have an object whose proper size is known, then the angle it subtends is the angular diameter the ratio of the proper size to the angular diameter distance. Or what is more useful is that if I know the angular diameter distance and if I can measure the angle it subtends, I can get the proper size. Okay. And usually there are certain things called standard rulers for which we have some idea of what the proper size is, and the angle can be measured. This is where the angular diameter distance is particularly relevant. Okay. And the angular diameter distance is defined as the ratio of Sz S to 1 by 1 plus Z. Okay, this we worked out in the last class. And if it's spatially flat, then it is R by 1 plus Z. So this picture shows you the angular diameter distance for different cosmological models. The picture on the screen shows you the angular diameter distance, how it varies with redshift for different cosmological models. So you see that for all the models it has a maxima somewhere around between 1 and 2, and then it falls off. And again you see that the angular diameter distance in this redshift range between 0 to 6, LCDM is much larger, is larger than all of them. Okay, LCDM and OCDM are actually quite close nearby, whereas the ones which have significant amounts of matter, omega matter is close to 1, the distances are much smaller, considerably smaller. And if you look at the behavior over a large redshift range, this is what it looks like. And at large redshifts, the open CDM model has a larger angular diameter distance compared to the LCDM, and LCDM has larger than the standard CDM or the curved one with a negative curvature, with a positive curvature. Okay, so this is the angular diameter distance. It basically refers to angles. The next thing that we were discussing in the last class is the luminosity distance. And I had told you what the luminosity distance is based on. It is based on the relation between luminosity and the flux. So now let us derive the luminosity distance. Okay, RL. So let us consider a source whose luminosity, the amount of radiation it emits in the frequency range L nu emitted, delta nu emitted. This is the energy emitted in the frequency interval. So energy emitted in the time interval per time. Okay. So this is L nu is the energy emitted in the frequency interval delta nu e basically. Okay, so there is a source over here which is emitting radiation, and this is the luminosity in a particular frequency interval. So if I multiply it with the frequency interval, I get the amount of energy it radiates per unit time. Okay, and we want to find what will be the flux that will be measured by an observer over here. Okay, how is the the derivation done? The derivation is done that you consider the photons that come out of here. They will be distributed over a sphere like this, and you divide that by the area of the sphere, you will get the flux. The time over which it is emitted and the time over which it is received is the same usually, when not in the usual context. Say you have a 100-watt bulb and you want to do it. Okay, but here you see the time interval also gets changed because of the expansion of the universe. So let us put in the time interval, and the frequency also gets changed because of redshift. Okay, so let us now calculate the relation between the luminosity and the flux, taking into account all of these. So to do this, let us calculate first the number of photons that were emitted. The number of photons will not get changed. Okay, so the number of photons that were emitted, delta n emitted, is equal to, in a time interval, so this is the number of photons that were emitted in a time interval delta t e in the frequency interval delta nu e, is given by L nu e delta nu e delta t e divided by h nu e. This is the number of photons that were emitted in the frequency interval delta nu emitted in the time interval delta t emitted, right. So I have to, this is the energy that was emitted in this frequency interval and time interval, divide by the energy of each photon, I will get the number of photons. Now the same number of photons that were emitted will propagate out and they will pass through a surface of some radius at some later time. So the same number of photons will be received over here, and to determine the flux at the observer, what I have to do is I have to divide delta nu delta n emitted by, I have to multiply this with the frequency of each photon. So the frequency of the photon would have changed by the time it comes from here to here. It will be h into nu observed. This is the total energy that is crossing this surface, and it will be received by an observer over here over a time interval delta t observed over a frequency interval delta nu observed. This will be the flux in the frequency interval observed over here. Now question is, what is the ratio of these emitted frequency and observed frequency? We have already worked this out. Oh sorry, divided by the area of the sphere, and the area of this sphere is going to be 4 pi into s, the area of the sphere is going to be 4 pi into s squared, right, that is the area. It is not going to be c delta t, it is going to be 4 pi s square. That is how you calculate area in cosmology, right. The distance is r, the distance from here to here is r, so the area is 4 pi s square, not 4 pi r square. Okay, so this is the flux, and we know how to calculate s. So the situation that we are considering, the observer is at a redshift 0, the source is at a redshift z. So we know what this r is, we know what s is a known function, okay, and we want the physical area here, this is the comoving area, we have to divide it by the physical area, the proper area, this will have to be multiplied with the scale factor squared, this will give me the comoving area, but the scale factor at present has a value unity, so we will not, okay, so actually there should be a naught square here also, right. This is the area of the sphere at the instant when the observation is done, but a naught we have assumed to be 1 because the observer is at present, so this is 1, this will give us the flux in the interval delta nu. So now you see we have to determine, what is the ratio observed frequency to emitted frequency, okay, what is the ratio of the, okay, let me put this here. So what we will have is that the flux is equal to the luminosity and then I will have here the nu observed by nu emitted coming from this and this. I will have delta nu observed by delta nu delta nu emitted by delta nu observed, delta T emitted by delta T observed into 1 pi 4 pi s square z. Okay, that is what we have. So I have just put this delta n over here. So I will have the ratio of delta T emitted by delta T observed, nu observed by nu emitted, and delta T and delta nu ratios. Okay, so this is what I will get. Fine. Now we also know that nu observed by nu emitted is equal to 1 plus z, which is also equal to T emitted by T observed. Okay, we have worked this out, how delta T emitted, how time intervals change, because it is light that is propagating. So we have worked this out right in the beginning. So you see that this ratio will cancel out with this ratio, and this ratio will give me a factor of 1 plus z. So T emitted, delta T emitted by delta T observed delta T, right, this will be the inverse of this. So delta T emitted by delta T observed, correct. So what we have here is that the flux have I got this correct? No, this will be the other way around, sorry. The frequency of light as it propagates, what happens? Does it increase or decrease? From a distant source, will the frequency be higher or smaller? It will be smaller, right? So the observed frequency will be less than the emitted frequency. Observed wavelength is more, so it will be 1 by 1 plus z, and the time interval is opposite to the frequency. Okay, so there will be a factor of 1 plus z minus 1 here. So what I will get is 1 plus z, yes, z square. Okay, compare this with the definition of the luminosity distance. This is 4 pi dl square z. So what we get from here is that the luminosity distance dl is equal to square root of 1 plus z into sz. Okay. This is if you are dealing with luminosity and the flux per unit frequency, per frequency interval. Now quite often you do not deal with this, what you deal with is the bolometric luminosity. So what is the bolometric luminosity? The bolometric luminosity is the total luminosity integrated over all frequencies. Okay, so this is the bolometric luminosity, which is L nu integrated over d nu. Similarly, the bolometric flux is going to be F nu integrated over d nu. Now the point to remember is that here the integral will be over the emitted frequency. and here the integral will be over the observed frequency. After all, this is what you observe. You see the light that you observe here, this is the observed frequency, this is the emitted frequency. They are not the same. You are actually, what this gives you is the relation between the luminosity at a certain emitted frequency and the flux at another observed frequency, some observed frequency which is different, and these two are related, the frequencies are related through redshift, that redshift formula over here, okay, which we just here, this formula. So if you take this expression and integrate it, let us say we integrate it over the observed frequency. So we integrate this over the observed frequency, then what we get is that the flux, the volumetric flux is equal to, so I will have 1 by 4 pi 1 plus z s square, that is what I will have here, and then I have the integral, the luminosity d nu observed, right, because I have integrated this over the observed frequency, and this I have to write in terms of the emitted frequency, because I know the luminosity, that volumetric luminosity is the integral of this over all emitted frequencies. So I have to then multiply, rather divide this. No, what do I have to do? I have to, so the flux can be written as 1 by 4 pi 1 plus z square s square z L nu emitted d nu emitted, okay, because I have to multiply this with a factor of 1 plus z and I have to divide this. If I multiply this with a factor of 1 plus z, this becomes the d nu emitted, and this thing is the volumetric luminosity L. So we see that if you use the volumetric flux and the volumetric luminosity, then the luminosity distance is equal to 1 plus z into the okay, and throughout our discussion we shall be using this definition. So this is if you use the volumetric luminosity and the volumetric flux. So let me show you how this varies with redshift. So this picture, this graph over here, the graph on the computer screen shows you how the luminosity distance varies with redshift for the different cosmological models that we were discussing. So you see again, the ones which have large amounts of matter dominated, both these models, the behavior is quite different from the model where omega matter is 0.3. Okay, and you see again here there are differences between the open CDM and the LCDM model. This shows you the same thing, how the luminosity distance varies with redshift over a large redshift range. Okay, so we see that the distances which are the distances which are important in observational cosmology are essentially the luminosity distance and the angular diameter distance. These are the two things which are important in observational cosmology. The distances that we have been discussing till now, the luminosity distance, the angular diameter distance, comoving distance, etc., all of them have the property that at low redshifts we recover the Hubble's law. So, this is a very important thing. So, all the laws at low redshift recover Hubble's law, and you can all the distances you can check that from the formula. And these, if you have observations at low redshift, then these observations do not depend on the cosmological model, they only depend on the value of h naught, which sets the overall length scale. C by h naught sets the overall length scale. So, the basic idea that we are going to discuss now is how to determine h naught. And observation at low redshift can be used to do this. So, if you can measure the distances to different galaxies independently and the redshift independently, if you can measure redshift and distances independently, you can then determine the value of the Hubble parameter. I have also told you several classes ago that determining distances is the most difficult thing in cosmology. You can infer the distance from the redshift, that is easy, but independently determining distances is extremely difficult. So, let us now take a look at this. So, this is what Hubble had done to start with. Hubble had measured distances using Cepheid variables, distances to galaxies, and he had measured the redshift from the spectra. And this is a picture of Edwin Hubble, and he had measured these two quantities, and he found that a straight line that they have a linear dependence. Hubble's observations unfortunately were based on very low redshift. So, he had only a few galaxies located very close to us, and the slope that he got was too high, far too high. He got a slope of around 400, which brings down the entire distance scale of the universe. So, let us now take a closer look at this, the future developments, the subsequent developments since Hubble. The basic problem in determining the Hubble parameter lies in the fact that you have peculiar velocities, and the notion of a peculiar velocity is something new. So, let me spend a little time discussing this. So, in the picture that we have learned, the observer here and this observer will see that all the galaxies are moving away with a velocity which is proportional to the distance, and this velocity in the nearby universe, and this velocity can be interpreted as the redshift. That is in the nearby universe. If you look at the entire picture, then it is better to interpret it in terms of the scale factor, but in the nearby universe this is fine. Now, this is the component of velocity due to Hubble expansion, you can think of it like that. Now, in reality, in addition to this expansion, the the velocity due to the expansion of the universe, the galaxies have other components of velocities also, and this other component is called the peculiar velocity. So, peculiar velocity is by definition the actual velocity of a galaxy minus what you expect from the Hubble law. This definition is in the nearby universe. If further away, it gets slightly modified, but it is essentially this. It is the deviation from the Hubble expansion. Why are there deviations from the Hubble expansion? from the motion predicted by the expansion of the universe? These deviations arise because the universe is not exactly homogeneous and isotropic. There are deviations, and some parts of the universe have more matter some parts have, so this is more matter, some parts have less matter, so I will put a different color, and the places which have more matter exert an extra force on this galaxy, for example, or a place where there is less matter will exert an extra repulsive force. So the analysis till now has assumed that the universe is homogeneous and isotropic, but if there are deviations, these will cause deviations in the velocities also, and these are what are called peculiar velocities. For example, Andromeda galaxy is not moving away from us, it is moving towards us. Why? Because the in the neighborhood between our galaxy and Andromeda galaxy, in this region there is excess matter compared to the average density of the universe, which is causing the Andromeda and our galaxy to coalesce, come together. Okay. So there are peculiar velocities in the universe, this is an observed fact, and the peculiar velocities typically have speeds of the order of few hundred kilometers per second. So you could take a typical speed to be 300 kilometers per second, and if you convert this to redshift using z is equal to v by c of the order of v by c, then you get that this corresponds to a redshift of 0.001. I have chosen 300 so that this comes out to be, the division is easy. So peculiar velocities can produce, will contribute to the redshift, and the contribution will be of the order of 10 to the power minus 3. So the redshifts that you see have a contribution due to the Hubble expansion. In addition, they have a contribution due to peculiar velocities that let us call it the peculiar redshift, peculiar velocity by c, and this is of the order of 0.001, that is what we just saw. This will introduce errors in the redshift. The redshift that you measure will not be just due to expansion, it will have a contribution due to peculiar velocities. So this will be reflected in an uncertainty in the Hubble parameter, because what you will do is you will measure the distance, you will measure the redshift and look at the ratio. If the redshift has some other contribution not due to the expansion of the universe, that will be reflected in an uncertainty into the Hubble parameter, and we would like the uncertainty in the Hubble parameter in this, we would like the error due to this peculiar velocity to be less than 10%. Let us put a restriction like this. If you want this condition to be satisfied, then you have to look at a redshift of 0.01. If you consider a galaxy at a redshift of 0.01, then the effect of the peculiar velocity we know is going to be within 10%. Okay, and a redshift of 0.01 corresponds, so you have to look at galaxies at a distance which is more than 0.01 into c by h naught, which comes out to be around 30 megaparsec. So for a reliable determination of the Hubble parameter, you have to look at this relation at distances beyond 30 megaparsec. Only then will the contribution of the uncertainty due to the peculiar velocity be less than 10%. Okay. So you have to look pretty far away, you cannot look at just the nearby galaxies to determine the Hubble parameter. That is the first thing that we have to realize. Now once you look at galaxies at 30 megaparsecs, once you look at galaxies at a distance of around 30 megaparsec, you can no longer identify Cepheid variables at that distance, you can no longer identify the stars. So a galaxy at that distance, you cannot identify individual stars, it will look like a fuzzy thing in the sky, that is all, you will not be able to make out the stars. So one has to look at other things, other quantities to determine the distance. Other important thing is that if you can push this exercise to larger redshifts of order 1, at redshifts of order 1 we have seen that the distance, the different distances, for example the angular diameter distance, the way it varies with redshift depends on the cosmological model. So if you can measure the distance as a function of redshift, you can determine which cosmological model we are in. So you can essentially determine the values of these omega density parameters, because the distance will be different for different density parameters. You will get one value, so you will know which one we live in. Okay, that is the basic idea. So, this brings us back to the issue of the distance ladder, the cosmological distance ladder, and we have already discussed the cosmological distance ladder. To some extent we have learned that you can use Cepheid variables to determine distances out to galaxies which are near us. So, the globular clusters and nearby galaxies where you can make out stars, you can use Cepheid variables to determine distances. Now, let us look at the cosmological ladder again. So, we have to now determine distances beyond 30 megaparsec. That is the basic problem, and it is not possible to directly jump to 30 megaparsecs because you can't see Cepheids there. So, you do not know how to do it. Okay. So, you have to again extend your ladder, put various steps in between which overlap. So, let us go through this. So, we will now start the discussion from the larger scales, other way around, and work back to the place where you can use Cepheid variables. So, the basic idea is that at large distances like 30 megaparsec, you can use properties of galaxies. That is the only thing that you can use by and large, properties of galaxies. Okay. Now, question is that if you look, just take the luminosity of a galaxy. If you assume that all the galaxies have the same luminosity and use them as standard candles. So, let us suppose we assume that I know the luminosity of all the galaxies, they are, let us say, same, and then if I take the flux and interpret that due to a variation in the distance, then I can get the luminosity distance if I can measure the flux, then and I can get the luminosity distance as a function of redshift. This will not yield correct results because the galaxy luminosities have a large scatter. They do not have, galaxies do not have a fixed luminosity. The galaxy luminosities have a large scatter, they come in a large range. Okay. So, our galaxy, for example, has a luminosity of around 10 to the power 11 times the luminosity of the sun. That is the number of stars in our galaxy. There are galaxies which are considerably fainter and considerably brighter. So, the variation in the flux cannot be related to a different to the distance. Okay. So, one has to look for other means of determining the luminosity of the galaxy, and the basic idea is that one has to look at correlations between the luminosity and the properties, other measurable properties of the galaxy. Okay. So, you cannot measure the luminosity, but you can, there are other quantities which you can directly measure, or you cannot measure the length of a galaxy, but there are other quantities which you can measure, and if you can correlate the length to those, then you can use this to determine the get standard candles and rulers. So, let us first start off with elliptical galaxies. So, we have already learned that the distribution of specific intensity in an elliptical galaxy looks like an ellipse, and these are believed to be ellipsoids, 3-dimensional ellipsoids. Okay. Now, the specific intensity variation inside the galaxy away from the center. So, specific intensity obviously falls off as you go away from the center. This fall off of the specific intensity away from the center, it is found, is well described by what is called de Vaucler's r to the power 1/4 law. So, the way the specific intensity, surface brightness, falls off as you go away from the center is well described by this law, I naught exponential minus r by r naught to the power 1/4. Okay, this is called de Vaucler's r to the power 1/4 law. And the specific intensity is something that can be measured, because the specific intensity does not change as the light propagates. Well, that is not precisely true in cosmology. In cosmology, the specific intensity will change because of the redshift. Okay, but that we know the redshift, you have measured the redshift of the galaxy, so you can predict what the specific intensity is when the light is emitted. Okay. So, we can measure the central specific intensity, for example, of a galaxy. That is not difficult to do. Another quantity that you can measure is the central velocity dispersion, sigma v. What do we mean by velocity dispersion? So, this galaxy is an ellipsoid like this, let us say, and it is a collection of stars. Elliptical galaxy. In an elliptical galaxy, the stars are moving randomly in different directions, like a gas at some temperature, and it is this random motion that prevents the galaxy from collapsing. Otherwise, the galaxy would have collapsed under its own weight. Okay, so there are random motions which prevent it from collapsing, and the sigma v. What is sigma v? So, we are observing from somewhere over here, large distance away, and we can measure the line of sight component of the velocity. So, we will be able to measure only the component of the velocity along our line of sight due to from Doppler shifts. So, if you can look at the spectrum, if you look at the spectrum of this galaxy in some line, then the line will be some broad thing like this, where the width is determined by the velocity dispersion. Okay, you will not be able to make out individual stars typically, but you will be able to make out, you will get a broad line due to the random motions of the galaxies. Okay, the width of the line will reflect the random motions of the galaxies, because each spectral line will not be at the same place, it will be shifted due to Doppler shifts. And the mean, the RMS, the variance, standard deviation of these velocities can be estimated from the line width, and that is what is sigma v, the velocity dispersion. Okay, so it is v minus v mean, the mean value of this squared. Okay, that is how you calculate the mean square RMS value, deviation from the mean value. So, you can measure the central velocity dispersion. So, these things can be measured, I naught and sigma v, and it has been observed that there are some relations which are referred to as the fundamental plane. So, there is a relation which is referred to as a fundamental plane. So, what is this fundamental plane? These are essentially correlations between different galaxy properties. Here the three properties that we are looking at are the total luminosity of the galaxy, the specific intensity at the center, surface brightness at the center of the galaxy, and sigma v. And it is found purely empirically that the luminosity is proportional to the central specific intensity to the power x and sigma v to the power y. So, this is a plane in a 3-dimensional space which has a luminosity, central specific intensity, and sigma v as the axis. It is called the fundamental plane relation. Okay, it is called the fundamental plane basically. So, the galaxies lie in a plane in this space of luminosity, central specific intensity, and sigma v. So, if you can, in principle, if you can measure the value of this central specific intensity and the velocity dispersion at the center, you can determine the luminosity. Okay, because galaxies all lie on a particular plane in this space of these three parameters. Okay, so this is one possible thing that you could use. Another possibility is what is called a sigma dn or dn sigma relation. Dn is the radius of the diameter or diameter of the galaxy, dn, and it is defined in such a way so that the average specific intensity inside this radius has a particular value. Okay, so you have an image of a galaxy, you find the diameter inside which the mean specific intensity has a particular value. Okay, so that it is found that that is related to the velocity dispersion. So, if you can measure the velocity dispersion of the galaxy, then you can predict what the length scale corresponding to this d, you can predict dn, and from the image you can measure the angle that this subtends. So, you know this length, you know the angle, so you can determine the angular diameter distance. Well, at low red shifts they do not differ, so you can determine the distance. Okay, so essentially if you can measure sigma v, you can predict the diameter of the galaxy, and you can measure the angle from the image, then you can use this to determine the distance. Further, there is another possibility which is called the Faber-Jackson relation. This relation relates the luminosity to the central velocity dispersion. So, these are all empirical things, findings. Some of these can be justified. There is a physical basis for some of these, which depends on the which is based on the you have physical arguments for some of these relations based on the virial theorem, because we know that the galaxy is in equilibrium. So, the kinetic energy should and the gravitational potential energy are related, one is half of the other. From there you can find that such relations should exist, and these are observationally found. So, they allow us to determine either the luminosity or the diameter of the galaxy from measured quantities. For spiral galaxies, so we have also learned that there is another type of galaxy called a spiral galaxy. In spiral galaxy, we have a disk, and the disk is rotating. So, for a spiral galaxy, it is found that again the rotational velocity is related to the luminosity, and this is called the Tully-Fisher relation. And these observations so this can be done either in optical or in infrared or 21 centimeter neutral hydrogen, which we have discussed. Okay. So, here again, if you can measure the rotational velocity, which is easy from Doppler shift, you can predict the luminosity of the galaxy. So, let me briefly summarize. We have what we have learned in the latter part of today's talk. We have learned about how we can use galaxies as either standard rulers or standard candles. Okay. So, let me bring today's lecture to a close over here. We shall resume our discussion from here in the next lecture.